Today we're going to cover two sections. Exact equations is 2.4, and then section 2.5 is almost exact equations. So it's not too much change from 2.4 to 2.5. So what is an exact differential equation? Usually they're written in differential form, so m dx plus n dy equals a constant or equals 0, and that's exact if there's a big F with the partial derivative of f with respect to x equal to m, that's the coefficient of dx, and then the partial derivative of f with respect to y equal to n. So here's an example. This differential equation right here is exact, and I've found a big F. Big F is x squared y squared plus x. Now, if you take f sub x, you get 2xy squared plus 1. That's this function here. So this is fx. And then if you take fy, you get 2x squared y. So this is fy. So that differential equation is exact. And a solution is big F equal to c. And I go through the particulars of that at the end of the lecture notes if you want to see that. But this is the format of your solution. So this brings up two questions. One, how do we know when a differential equation is exact without actually having to find a big F? And two, if we want to find big F, how do we find it? So to answer question one, we have this first box here. There's a test for exactness. The test is my is nx. If that's the case, then this differential equation is exact. Now, I don't know if you remember, but in Math 2b, we had a vector field of the form m, n, and there was a test for a conservative vector field, and the test was n sub x had to be equal to m sub y, and the mnemonic device was all be conservative next May. Well, that's this exact same test. M sub y is nx. Just I wrote it differently here, but it's the same test. All right, so we're going to go through three examples, and we're going to determine if these differential equations are exact, linear, and or separable. And I want to illustrate to you that these conditions are all distinct, so one doesn't imply the other. So first one, is this differential equation exact? So let's write down what m is. M is always the coefficient of dx, so root y. N is the coefficient of dy, and you have to be careful. It's plus n. So if this is a minus, then n is going to be negative, whatever this function is, x squared minus 1, because we have to write that as plus negative x squared minus 1 dy. All right, so m sub y is 1 over 2 root y, and n sub x is negative 2x. Those are not equal, so that's a big no. Linear. We're going to determine if this is linear with x as the independent variable. So I'm going to divide this equation through by dx. Root y minus x squared minus 1 dy dx equals 0. I don't have to rewrite that or go any further. I can see this is clearly not linear because I'm not allowed to take the square root of y. So that's no. Don't have to do anything more. Separable, when I'm trying to determine if a differential equation is separable, I like to move the differentials to different sides. So I'm going to leave the dy on the left, x squared minus 1 dy. Then I'm going to move the dx term, negative root y dx, move that over there. And then can I separate these variables using multiplication and or division? Yes, I can. First of all, let's multiply both sides by negative 1. And then let's move our y's over here. 1 over root y dy is 1 over x squared minus 1 dx. So that's a yes. And I separated the variables. Okay, next one. now on these examples, I've already done some of the grunt work for us. I've written down what m is and what n is. My is x, and x is 0, so that's a big no, because those are not equal. Is it linear? Yes, but the instructions are to write it in the format of a standard format from our section on linear differential equations. So dy dx plus p of xy, so that's xy equals q of x, 0. So this is a yes. Is it separable? I would say definitely yes. I moved the dx term over, and now I can divide both sides by y. 1 over y dy is negative x dx. All right, and last one. Is it exact? Well, m is 2xy plus 3, so m sub y is 2x. There's a typo there. This shouldn't be x squared minus 1 because this is just x squared. So take out that minus 1. N sub x is 2x. I copied this example from the next page because we're going to solve a differential equation similar to this. So this is yes. Is it linear? I would say yes. Let's move the 3 over. So, and I'm going to put the x squared dy dx first, and then plus 2xy equals negative 3. And now if I want it in standard form, I divide through by x squared, and I get dy dx plus 2y, let's see, if I divide by x squared, I'll get 2 over x times y. So my p of x is 2 over x equals negative 3 over x squared. So that's a yes. Y-E-S. Is it separable? Unfortunately not. There's no way I can get my y's over here and my x's over here because of that plus 3. So not separable. All right, so that's question 1. How do you know if you have an exact differential equation? And if it's in differential form, just do the test, is my equal to nx? Step 2, if it is separable, if it is exact, how do you find a solution? So first of all, your solution format is going to be big F equals C, if you can find big F. And here's how to find big F. First of all, this, by supposition, is f sub x, and this is fy. So if you're trying to recover f, take m and integrate with respect to x. That will give you f up to a constant, and the constant's going to be a function of y, so g of y. Then take the partial with respect to y of your answer in part 1, all right? And then set that equal to n, because again, by supposition, n is f sub y. That will give you g prime of y, and you can recover g in step 3 by integrating with respect to y. If g prime of y equals 0, so then g is a constant, take the constant to be 0. There's a couple examples that you're going to do at home where g is actually equal to 0. And then the solution format is important. Don't write f of xy equals blah. You have to write the function that you find equals c. So it's a level curve. So this is probably confusing to you. You have no idea what I'm talking about. So let's make it very clear by doing a few examples, and we'll go through these steps one by one, and you can see what I'm actually talking about. So example 1. By the way, these 3 examples are exact, and I'm stating that right in the problem. Sorry about that. So we don't have to verify that my is nx. In your homework, they want you to verify that before you solve. But you can see clearly that this, in this case, my equals nx is 2x. So this is exact. So step 1, this is my m, and this is my n. M, so big F, and you can write big F on your homework and on test. I don't care if you write big F or big F of xy. It's up to you. One's shorthand, one's not, but I need to see the big F there. Is the integral of 2xy plus 3 dx. So we're going to integrate m with respect to x, and so that would be x squared y, think of y as being constant, plus 3x plus a constant, but your constant is a function of y. Okay, that's step one. Step two, take the partial with respect to y of your f in step one. So that gives us x squared plus 3, hang on a second, not x squared plus 3, x, so taking the partial with respect to y, so 3x is a constant, so that partial is 0. So I'm going to get x squared plus g sub y, the partial of g with respect to y. So step two is 2 steps. You take f sub y, and then you set it equal to n. So here's n, x squared minus 1. So there'll always be some matchup. The x squared and the x squared cancel, and that tells me that g sub y is -1. So step 2 will determine g, well, it will determine the partial of g with respect to y. So step 3, you can recover g by integrating with respect to y. G of y is the integral of -1 dy, which is negative y. Okay, now put that into this guy. So big F is equal to x squared y plus 3x minus y. Okay, here's the mistake that a lot of students make at this point. They'll circle that and move on. That is not the answer, okay? The answer is the level curve, big F equals C. So step 4, the solution has to be this format, big F equals C. So take your big F and set it equal to C, x squared y plus 3x minus y equals C. That's your answer. Okay, let's do another one. Once you do a bunch of these, the steps will just become natural and you won't even have to think about it. So step 1, big F, this is exact, big F is the integral of cos x cos y plus 2x dx. Okay, so y is constant, so cos y is constant. So this is just going to be sine x cos y plus x squared plus a constant g of y. All right, step 2, take the partial of that with respect to y. So the derivative of cos y is negative sine y. So f sub y is negative sine x sine y. The partial of x squared is going to be 0. And so we're just going to get plus g sub y. And we're going to set that equal to n. Now be careful. N is not positive sine x sine y plus 2y. It's negative because there's a minus here. So n is negative sine x sine y minus 2y. So kill. That tells me that g sub y is negative 2y. So step 3, I can recover g. G of y is the integral of negative 2y dy, which is negative y squared. So put that up here into big F. Big F is, just be careful when you do this because it's easy to just look back and plug into the wrong thing. So make sure you're plugging into the correct expression. Sine x, that's why I want you to label everything. Cos y plus x squared minus y squared. And that's not your answer because there's a step 4. So step 4 is set big F equal to a constant. Sine x cos y plus x squared minus y squared equals C. Okay. Next example, we're going to do the same thing, except now we have an IVP. So we're going to have 5 steps. Steps 1 through 4 are identical. Step 5 is to determine C. So step 1, this is just good practice integrating. Big F integral of 2 over root 1 minus x squared plus y cos xy dx. All right, and I integrate, I get 2 sine inverse of x. And then if I'm integrating with respect to x, y is a constant. So a 1 over y comes out, and I'll just get plus sine xy. Make sure you follow that, plus g of y. Step 2, take f sub y. So 2 sine inverse of x, that partial will be 0. And then I'll get partial with respect to y. X is a constant, so x cos xy plus g sub y. And set that equal to n. N is x, this is n up here, x cos xy minus y to the negative 1/3. And so this tells me, and you'll always get matchup here. If you don't, just look back. You probably made a mistake somewhere, forgot to take f sub y or something like that. These guys kill each other off, and g sub y is negative y to the negative 1/3. So step 3, g is the integral of negative y to the negative 1/3 dy, which is, add 1, you get 2/3, flip that, 3/2, negative 3/2 y to the 2/3. So big F is 2 sine inverse x plus sine xy minus 3/2 y to the 2/3. So our general solution, we're not done. Step 4, we're just going to write down the general solution. General solution is big F equals C. So 2 sine inverse x plus sine xy minus 3/2 y to the 2/3 equals C. All right, and step 5, now I'm going to use the initial condition that y of 0 is pi over 2. So everywhere I see an x, I put in a 0. Everywhere I see a y, I put in a pi over 2. So 2 sine inverse of 0, which is 0, plus sine of 0, which is 0, minus 3/2 pi over 2 to the 2/3 equals C. So that tells me that C is negative 3/2 pi over 2 to the 2/3. So just take that and plug it back into your general solution, and that'll give you the IVP solution. 2 sine inverse of x plus sine xy minus 3/2 y to the 2/3 equals C, but C is negative 3/2 pi over 2 to the 2/3. All right, so that is exact differential equations. What if you have an equation that's not quite exact? It's possible to make it exact, not always, but sometimes you can make it exact. So if you don't have an exact differential equation, but this expression is a function of x, then you can multiply both sides of this equation by an integrating factor to make it exact. If that's not the case, you could try this one. If nx minus my over m is just a function of y, then you can find this integrating factor, multiply through, and you'll get an exact equation. So let's look at an example right here. So first of all, this equation is not exact. I looked at my, got 2x, but nx was negative 6x. Those are not equal, so this differential equation is not exact. Now, 1 and 2 are pretty much equal weights. I always start by checking 1. If 1 isn't true, I check 2. You don't have to memorize these formulas. I'll give them to you if you need them on a test. You just won't use them enough to have to memorize them. You do have to memorize the process for finding the solution of an exact differential equation that we just did, but this you do not have to memorize. All right, so I started with 1. I looked at my minus nx over n. Now, that turned out not to be just a function of x. I wasn't able to cancel the y's and just get a function of x. So I moved on to expression 2. nx minus my over m. Sometimes you have to do some algebra here in order to make this work, but I was able to cancel the x's and I got negative 4 over y. That's a function of y. So I'm going to make this integrating factor. Let mu of y equal e to the integral of negative 4 over y dy. So I'm just using this formula right here. E to the integral of that expression. That's e to the negative 4 ln absolute y, which is e to the ln of 1 over y to the 4th, which is positive. I don't need the absolute value. But even if I had the absolute value, I could get rid of it, just like when we solve linear differential equations. So this is 1 over y to the 4th. So I'm going to make a new equation by taking my old equation and multiplying through by this expression, 1 over y to the 4th. So here's my new equation. 2xy over y to the 4th is going to be 2x over y cubed dx plus y squared over y to the 4th is 1 over y squared, and then minus 3x squared over y to the 4th dy, and that equals 0. Let's just check, make sure that's exact. If it's not, we did something wrong. So my, think of this as 2x y to the negative 3. So that would be negative 6x y to the negative 4. And n sub x is, bring down the 2, negative 6x over y to the 4th. Those are the same. In one case, I'm using negative exponents. In the other case, I'm not, but those are the same. So I have an exact differential equation, and I can go ahead and solve it just like I did on the previous page. So 4 steps. 1, big F. And so you'll never go back to the original differential equation. You'll never go back there. So just cross it out and move on. This is our new equation. It's possible to lose solutions when you multiply by an integrating factor. And in this case, we actually do lose a solution, but I'm okay with that. So big F is the integral of 2x over y cubed dx, which is x squared y to the negative 3 plus g of y. So step 2, take the partial with respect to y. We get negative 3x squared y to the negative 4 plus g sub y. Set that equal to n. Excuse me. N is, I'm going to switch to negative exponents. Y to the negative 2 minus 3x squared y to the negative 4. So this cancels with that, and I get g sub y is y to the negative 2. So step 3, g of y is the integral of y to the negative 2 dy, which is negative 1 over y. So my big F is where am I? X squared y to the negative 3 plus g of y, so minus 1 over y. And then my final answer, I need to set that equal to a constant. So my solution is x squared y to the negative 3 minus 1 over y equals c. Okay, so you only have a couple of those in your homework where you have a non-exact differential equation. And for practice, oh, here, by the way, I'm talking about losing a solution. We did lose a solution. For practice, so I'm stating this as exact, so you can go ahead and solve this using steps 1 through 4. Actually, there'll be a step 5 because this is an IVP. And then this one is not exact, but I'm telling you which integrating factor you can use to make it exact. All right, and that's the end.